Invitation to come speak at the workshop. Yeah, it's been a really nice event and very nice synthesis of a lot of different ideas in these overlapping areas. I was thinking about sort of what would kind of fit with the themes of this, and I want to talk about two recent projects that are sort of broadly about trying to build theoretical models of humans and AI interacting with each other on shared tasks. And particularly, I think the common theme in them is delegation, the handing off of tasks from one entity to another, and sort of to think about different ways in which delegation works. I think one of the reasons why there's so much work in this area, and this workshop's doing a nice job of pulling many threads together, is just how many different control flows there are for how delegation might work, right? Even as soon as I have two entities, is it consultative? Is it, a direct handoff from one to the other? Does communication flow both ways, only one way? There are so many different ways that this can happen. And so actually, with that in mind, before I get to the two models, one is with Sophie Greenwood, Hoda Heidari, Levy, and Solon Barocas. The other is with Gali Noti, Sigal Oren, and Donahue, who is here. I can help me answer any questions that come up about it. I want to talk about some of the thinking that went into, like these models were trying to capture things that were taking place in the world. So I'll actually start possibly longer ago than any of these talks have started in 2018, which feels a very long time ago. If we think about sort of handoff from human to algorithm, the period like 2016, 2017, 2018 was this period of great excitement about, the sort of growing power of machine learning classification for many different problems. And there were a number of tasks that my co-author Senthil Mullainath and I were thinking about. Some of them you couldn't do delegation because it was literally forbidden by law, right? So in the case of judges making decisions in courtrooms, the Loomis versus Wisconsin decision literally says that the judge has to be the final decision maker, right? You are not allowed to delegate to AI. In other domains, obviously there's a lot of excitement about, controlled delegation, such as, maybe the canonical example being diagnosis from medical images. And I think the point there was, when you have a machine learning classifier on medical images, circa 2017, 2018, the first question you could ask is, which has better aggregate performance, right? The human doctor looking at the image and making a diagnosis, or the algorithm looking at the image making diagnosis. But that, of course, undersells the power of, more interesting control flows that this image could go through, right? It's not just passing task onto a partner, but it's really the sort of meta decision of which tasks to delegate, right? There's sort of these, right, you can delegate effectively if you have two things. One is a model of your partner and what they can do, what they do well and what they don't do well. And secondly, a partner who occasionally does better than you do. Right, and so in these medical examples, and there are many instances of this, the first thing you want to establish is some heterogeneity in the error patterns, right? That there literally are some things where the human has less error. I think there's a laser pointer. That's it. And some things where the human has more error. And secondly, an ability to sort of sort or rank, right? Either the human can do this or the algorithm can do this. And so, for example, in this particular 2018 era medical data set, the impressive thing was that the algorithm had some 90+% prediction accuracy, but if you ranked it by its confidence, the first error occurred at the 44th percentile into the list, right? You could pick off literally 40% at zero error before errors began showing up. Okay, so that was one thing from 2018. A second thing that happened in 2018 was there was a development in a different domain that caused my co-author Ashton Anderson and I to decide the time was finally right to do something that we had been wanting to do for a number of years, which was explore human AI delegation in a domain that had genuinely superhuman AI, right? We were looking for a domain where you had sort of, people who had this sort of amazing level of mastery. You had a century of scholarship, and yet, in this domain, we were, a good 10 years post singularity, right? Like we had unambiguously superhuman AI, and that domain, of course, is chess, something I came here in December and stood here and talked about. So I just wanted to review a little bit from chess to talk about sort of how this helped us with our thinking about human AI delegation. Obviously, chess has like a hugely long history as a topic of research, right? Newell and Simon worked on chess. Claude Shannon, shown here, presenting a trophy to the creator of Deep Blue, worked on chess. Alan Turing worked on chess, right? It was one of John von Neumann's examples in The Theory of Games. So it has this very, very long history. It's one of the few things to have been metaphorically called the Drosophila of more than one subject, right? Simon and Chase called it Drosophila psychology. John McCarthy across the bay called it the Drosophila of AI. The Drosophila, right, the fruit fly, the model organism that's so malleable you can do any genetic experiment that you want on it. And I guess what excited Ashton and me sort of around this time was that it was really becoming the Drosophila of this third thing, which was superhuman AI in a domain where humans were extremely motivated to sort of be cognitively excellent. And there's sort of a long history of this. And it's sort of interesting to look at this 20-year-long timeline as we all stand on the cusp of things that we are, viewing with sort of increasing apprehension, which the panel at 345 might get into, right? Like, are we at the cusp of, superhuman mathematics or coding and so forth? That it was sort of this 2-decade-long period from, the first time in a standard tournament that Grandmaster lost in chess to the, a machine that actually taught itself to play at a superhuman level knowing only the rules, right? That was 2 decades, and that's for a thing as simple as chess, right? You can imagine for other domains, right, this will either be spread out or compressed. But the approximate timeline, probably the most famous moment in this was 1997 when Deep Blue defeated Garry Kasparov in a 6-game match. There was then maybe a kind of 8-year period where it was still interesting to pit the best human in the world against computers. But that era came to an end around 2005, which was really the last recorded time that any human ever sat down across from a personal computer and beat it in chess. There was then a kind of 8 to 9 year period where people are like, but that's okay because the future is human AI teams in chess. And Garry Kasparov popularized this. It was so-called centaur chess, right? The creature that has like a human body and a horse body. And the idea is you and the engine will be like a centaur and you're going to use your human brilliance to strategically direct the engine. And that lasted for another 8, 9 years. The demise of centaur chess is a little hard to find because it sort of vanished with a whimper, not a bang. But by 2014, the problem was that the engines were just too good, right? If you're the best player in the world and you're paired with an engine, you're going to sit down and consult about what move to make. The best thing you can do is just do what it tells you, right? And probably the final, the final twist in this was there was an attempt to revive this around 2017 with a $20,000 prize fund. Teams entered, and it was won by a chess engine, right? So that kind of was maybe the final statement about this. And then 1 year later, and again, this gets me back to 2018, right? End of 2018, DeepMind releases, well, does not release, announces AlphaZero, which the open source community quickly rebuilt in an open source version called Leela, which became superhuman and became competitive with Stockfish, the best existing chess engine, purely from the rules of chess, just by teaching itself. Okay, so we were interested in this because there was a particular delegation problem that we were quite fascinated by in the context of chess, which is, imagine the following experimental setup, which chess engines are arguably, and in fact empirically, quite bad at. Imagine we're going to play chess as 2-person teams, okay? But this is not like centaur chess where you sit down with the engine, you consult, you discuss, you deliberate. Rather, we're just going to alternate moves, okay? The engine makes a move as white, you're playing white with the engine. So engine makes a move, black plays, and now you're the human, you make a move, black plays, engine makes a move, you just trade. But you cannot communicate. Right? You don't know why the engine made the move it did. Okay, I mean, you can also imagine doing this if you're just a regular player with a human chess grandmaster, right? Similar thing would happen. And of course, what's the problem here? The problem is that, right, so this is again just repeated delegation one to another. The problem, of course, is that the engine has this dangerous ability to set you up to fail completely because the engine doesn't know that this is what's going on. It just knows that it sometimes is asked to make a move and it dutifully makes the move. And the problem is, it sees a brilliant rook sacrifice and it makes it, knowing that there's a winning attack that's followed up, provided you do the right thing. Black takes the rook, comes back to you. You have to do the right thing, right? But of course, you don't know how to do the right thing, so you play some move, and now the engine's like, wait, now we're just down a rook and we're losing, right? So it has set you up to fail. It's not a very good partner for you. So it's sort of an interesting domain to think about how would I build a better version of this, right? We'd like a chess engine that tried to balance 2 things. One, it's still really good at chess, but also it only makes moves that you know how to follow up on, you, a weak human player, right? It does not ever set you up to fail, right? So it's a sort of like, right, it's a safer version to collaborate with by having a sort of model of what's going on with you. And we didn't really have a way, until you had a trainable superhuman chess engine, it was very hard to figure out how to do this, right? Like I can't tell Stockfish, please only make moves that I can understand, because Stockfish is just a deterministic, piece of C code that searches a game tree. But with Leela, we could do that, right? So Leela's a neural net that tries to evaluate chess positions. And so we want to create a self-play training loop for Leela. And so we need a stand-in for the human. Right? So we'd like to adapt Leela to play well in these conditions. So what you'd like to do is have it play 1 billion games and have some reward signal. And what Leela's going to learn, it doesn't quite know what the deal is. You haven't explained it to it in natural language, but it does know that when it makes these brilliant rook sacrifices, it tends to lose for some strange reason. And so it somehow, that goes back, that reward signal gets propagated back, and it tends to now steer away from edgy moves. And somehow the hope is it actually becomes a better partner for the human. So we'd like a sort of billion games of self-play with this. Now, the problem is humans don't usually have the patience to sit through 1 billion games of self-play. So we need something to stand in for the human. And so we built this, and now this is this project jointly with Reed McElroy-Young and Sid Sen, and with Ashton Anderson, built this chess bot named Maya, which the idea was to try to match human decisions move by move, right? To be as similar to human decisions as possible. And so, we took advantage of the fact that a site like Lichess is completely open. People publish their games by default, so you can easily find billions of chess games played by people of typical ratings, right? Ratings like 1100 or 1500 or 1900, which is sort of the big middle of the chess rating space. So we start with Leela, which has a head that evaluates things. We rip the head off of Leela, put on a head that is simply trying to, as close as possible, play human-like moves. Okay, so it's doing as much computation as Leela to train it, but in the end, it's all in the service of looking like a 1500 rated player, right? So in the spirit of some of the talks this morning about like how do we sort of simulate the human behavior, and it definitely becomes better at move matching, right? So this is for different ratings, and we have you can have Mayas of different ratings. The original Mayas you have to build rating by rating, but eventually it becomes a parameter. So you have like 1 Maya, and you have a tunable parameter for the rating. And at different ratings, right, it's best at matching that rating, right? So this is its move matching performance as a function of rating. These are the different Mayas and the curve of how well they do at move matching. And this is in comparison to Stockfish and Leela. There's actually a lot to be said about the sort of strange features of these things even, right? So, right, the whole point is like Stockfish, which is an engine you can play on your phone. It's open source. You can set the level, the search depth anywhere you want. If I set the search depth to 0, so it's making random moves, I will beat it. And if I set it to depth 20, it'll beat everybody on the planet. And so by some sort of intermediate value theorem, there's a level you can set it to where it will play evenly against you. But not because it plays in any sense like you. It's just that it sort of alternates really good moves and some really bad moves, and somehow you play it evenly. In terms of move matching performance, it's interesting that every Stockfish level is better at matching super strong players than weak players, right? Which is an interesting.
Calculate again what the accuracy.
Accuracy is, yeah. So I'm going to test it on games, and for each game, I'm going to ask it predict the next move. It gets 1 guess. So we're doing precision at 1. Big is good. So this is how often it matches. So we're doing precision at 1. So we play through the game. Next move is coming up. We show it the position, and we ask it, what move do you predict this player made?
But then I'm confused because you've got different Mayas for different ratings, but then you also have ratings on the axis.
Yeah, so let's take Maya 1500, which is this one. So Maya 1500, I could show games of people rated, let me explain the x-axis better. These are games played by people of rating 1000.
So Maya hasn't actually been trained on that.
Right,
Okay.
so we're doing a distribution shift where we show Maya 1500 games by people play rating 1000, 1250, 1500, 750, and so forth. And so it peaks at 1500 where it was trained, and it falls off in each direction. Yeah. Yeah, other questions about this picture? Yeah.
Again, you said ripping the head off, so like you're just retraining the last layer or something along those lines.
We keep a lot of the internal layers, and then
Right, you don't have enough data to retrain the.
It has this knowledge of chess, and then we tried it. Yeah. Okay, exactly. There are other things that maybe we'll never understand. I find this strange. Like, if I just take Stockfish, which is just this piece of code that does game tree search, and I ask how well does it match humans of all different ratings, right? So that's these colorful things here. So this is, I give it games of players rated 1000, 1250, 1500, and so forth. They all go up. This is Stockfish at depth 1, really weak. This is Stockfish depth 5. This is 9, 11, 15, and so forth. So in other words, it first gets worse, then gets better. The depth of Stockfish that least looks like a human is depth 5. I have no idea why that's true, right? Like depth 1 and depth 11 are kind of similar, and depth 5 is just not like humans. And it seems likely we'll never understand why that fact is true, but it's certainly an interesting empirical question. Okay, so you can use Maya you can actually use Maya just to analyze games, right? Like you can go over past chess games and ask like, here's a position from a pivotal game in the 1987 World Championship between Karpov and Kasparov, an important position where Karpov made this horrendous blunder. And you can ask, okay, so it's white to move. There are options for different moves. And I can ask, for every rating, what is the probability a player of that rating, according to Maya, would play each of these moves, right? And so if I like zoom in on that plot, I say, here are candidate moves. And here's Maya's estimate at each rating. Players rated 600, 1,000, 1,400, 1,800, right? Like this is like super strong amateur. This is like sort of, somewhere in here is like elementary school class champion. This is like, no offense if you rate 1,000, but it's kind of weak. Anyway, so, right. And these are the probabilities of, of these moves. Okay, and so the point is, actually, there's an interesting thing that Senthil, my co-author, Senthil Manath, and I had been looking for, and which actually is sort of, to some extent, borne out in this data, and this is something we're still looking at. Suppose I just showed you this plot, and I asked you, what do you think is the right move to play in this position, right? At all ratings up to 2,600, which is like super strong, like there are a few hundred people rated this, Maya predicts that the most likely move for all those ratings is queen to e2. And you look at this and you sort of suspect, correctly, that the right move to play is rook to c7. Why? Because it has the highest first derivative. It's the one that you're more and more likely to play the better and better you get. Right? So it's sort of weird that even if I cut the plot off here, right, simply looking at the sort of crowdsourced derivative on what weak play, what players up to here do, I'm making the correct prediction as to what the best move is, even though it's not the most likely move for any of them. Right? So there's a sort of interesting, like, hidden signal in here that I think is also kind of intriguing. Okay, so this was Maya. This was trying to match what the human is doing. You can apply Maya on Lichess. Actually, at this point, the 1100 version of Maya is the most played bot on Lichess. One other interesting thing to mention, if you look at Maya 1100, which tries to take the argmax, the most likely thing an 1100 rated player does in every move, and you look at it on Lichess, it's rated about 1400. Which again is sort of this interesting fact that Senthil, Jens Ludwig, Yuri Leskovic, and Hima Lakkaraju discovered with judicial decisions also, that often the model of the person is somehow doing better than the person themselves in terms of accuracy, right? It's somehow saying that if you take a model of an 1100 rated player, but you don't sample from their distribution, you always take the thing they are most likely to do. They actually play better than 1100, right? Because remember, we're taking the argmax every time. We're not sampling from the distribution. Okay, so finally, we can go back to this idea, repeated delegation. Now we have something with Leela and Maya playing against each other. And now we can finally say, okay, let's replace Leela. Let's now actually continue training Leela to be a good, yeah.
Can you just say again what the difference is between Leela and Maya?
Yes, so Leela is the super strong open source version of AlphaZero that plays at way superhuman strength. And Maya is the one that is doing all this stuff, which is trying to stimulate humans.
On a previous slide, you had Leela with some score numbers. What did that mean?
Yeah, this is Leela tuned to play at different ratings. Yeah, so.
How does that happen?
How does that happen? That's actually a very simple, there you just sort of dial down the depth that it's searching at, basically. Because even after you've trained the eval function on
Dial
Leela.
down the depth, then you sort of rank it or something?
Yeah, and then you play it against other bots and try to figure out a rating for it.
Got it.
Yeah, right. Like, Leela wants to play above 3,200, but you can always just dial down the search depth. Yeah.
And so when you say Leela in your next slide,
That's the one at
you
the
mean
super,
top one.
the super high rating, yeah.
Thank you.
Yeah, super powerful
And
Leela.
Maya, which one is it?
We did this mainly with Maya 1100.
Okay.
That's sort of the base one we usually use. Yeah. Okay, so the idea would be continue training Leela to now propagate the reward signal from losses, wins and losses in this setup. So it becomes a better partner for this. And the answer is it actually, so this is roughly what happens when you do all of this. You say, let's look at the following evaluation. So we're going to play against a Leela Maya team. Right, so again, Leela goes move by move. You show it a position, you say, what move would you make? It doesn't realize it's going to be handing off to a much weaker partner and doesn't plan accordingly. versus this partner bot where you train Leela to play in this setup. And so we're going to take different partners for Maya in a game against Leela and Maya as a partnership, okay? So I guess by symmetry, if it's Leela and Maya versus Leela and Maya, you're going to be 0.5 because they're symmetric, okay? The partner bot does what you want, which is 2/3 of the time it actually wins against the Leela-Maya pair. I say 2 of the times it wins. It's really that if I say a win is 1 point and a draw is a half point and a loss is 0 points, then your expected point total is 0.6565. Okay. Interestingly, the effect of Leela setting Maya up to fail is so strong that actually a Maya and Maya team, as in it's just 2 of them, actually still wins about, what is that, like 1/15 of the time. Okay. Okay. And then you look at these different things in solo competition. Obviously, Leela against Leela is 0.5. The partner bot is superhuman still, right? It wins about 14% of the time, right? So it's weaker than Leela, but not so weak that it always loses, right? Like a human will lose, right? A human will be, even the best humans will be 0.00 here. Whereas this is 0.14. So it is superhuman, just not quite as good as Leela. It has dropped down strength and become a better partner for Maya. And that's effectively what.
The second row changes 2 things. It just has the partner bot playing alone.
It has one of these things playing alone. That's right. I think that's the one thing it changes.
Okay.
It changes that one thing. So Leela playing alone against Leela, partner bot playing alone against Leela, or Maya playing alone against Leela. Yeah. Exactly. Right, and so this is sort of the question of, yeah, right. We have the weaker player, the better partner, right? This is like, right, you have like, yes, okay. So, and actually, in some sense, even if we go back to, like, I've been talking about this as delegation. Yeah.
There's one last thing you don't see in the bot. If partner bot plays with Maya, can it ever beat Leela, or is Leela always going to
Oh, I see. Partner bot and Maya
play against Leela by it?
I'm not sure we tried that. My sense is it will never win, but I don't know that we have a number for that. Yeah. Yeah, that's a good question.
It would be curious if it ever won, right?
If it ever won, yeah. I mean, the problem is, of course, Leela on its own doesn't have any apparent weaknesses for the. Yeah, but it'd be interesting if you make half the moves. Yeah, it's a good question. I'm not sure we've tried that.
Somehow bring Maya up to be competitive with something.
Yes.
Every once in a while.
Right. If you play, I mean, we've looked at sort of attenuation versions, right? So I said strict alternation, but what you can say is like Maya plays with probability p, and now there's this interesting thing where I reduce p more and more and more. So Maya plays more and more rarely. And so now the partner bot can be more and more adventurous because it's only rare that Maya comes in, right? And so you can look at what happens as I parameterize it continuously. Yeah. Yeah. My question about this.
I think maybe the version of the right-hand side would be various levels of Maya.
Oh yeah, we can put
And you
various
would say
levels.
you take Maya at like level 1100 or something with a partner bot, and like what various levels of Maya does that?
Yeah, I think the problem here is that, yeah, I see, we could parameterize it that way, yeah. That would also be interesting, I agree. I mean, even the strongest Maya has an enormous astronomical rating gap to Leela, but, so it's not clear how much difference that would make, but that'd be interesting to try, totally. Yeah, so what's interesting is, even just 2-player game, I mean, like, I've been describing this as delegation. Of course, 2-player games are in their own way a kind of adversarial form of delegation, right? Like, when you play a 2-player zero-sum game, I as one opponent, I delegate to my opponent, I'm trying to delegate a hard instance of the problem to them that makes it hard for them to find the next move. I mean, this too has been tried. So, also in Lichess, you can find Leela rook odds, which has been trained to play a rook down, right? It starts out a rook down. It recently just had this much publicized match against Hikaru Nakamura, the second strongest player in the world, where he agreed to play against Leela, where Leela gave up a rook at the beginning. And he lost the match 2 wins, 5 draws, 7 losses, I think, in a 14-round game. And the point was, Leela rook odds, if you just take away a rook from Leela and tell it to play, the problem is Leela evaluates the position as a dead loss. And the optimization landscape looks very flat to it. It doesn't really seem to matter to it. It's just losing. And so it'll do the thing you're never supposed to do if you're a rook down, which is start trading pieces down to an endgame, in which case humans can beat it. So the question is, how do you get Leela with rook odds to actually play well? against people? And the answer is you train it with Maya, right? So you take away the rook, and then actually this was fine-tuned by having it play a lot of games with Maya, whereupon it discovered to its surprise that it actually is possible to win a rook down if you play a certain way. Namely, you constantly go for attacks and you avoid trading pieces, which is what Leela rook odds ends up doing, right? So in some sense, like to get these engines to play really well in odds, you actually need to fine-tune them with something that looks like a human being. And again, it's a kind of adversarial form of delegation. Okay, so we've sort of expanded to 3 principles of delegation, right? Figuring out delegating instances, having a model of your partner, which all these things now do, and finally that you get to actually influence the instance that you actually give to your partner in some sense. Okay, so I want to start talking about a couple of models that we looked at, so this gets into a more theoretical part of the talk. But I want to sort of see if I can link this back. Now, the models, I think an interesting question is to sort of get the models to line up with the actual experiments here. I'm going to start with some very simple models, and then we can think about sort of what we might have to bring in. I feel like one of the simplest models of delegation, for us anyway, was a paper that we worked on for a number of years. We actually, Hoda Heidari and I started working on this sort of shortly after we were working on the chess experiments. And then we were joined by Sophie Greenwood, Karen Levy, and Solon Barocas. Let's imagine 2 agents engaged in a delegation problem. Okay, we'll call them the human and the machine, but it's really just 2 agents. The world is in some state x, and in state x, the optimal action is f star of x. But neither partner, the human or the machine, can perfectly observe the world, right? I can't perfectly observe the actual state of the world. I group it into coarse categories, okay? So when the world's in state x, the human sees, let's call it category C of x, from a list of human categories C1, C2, and so forth. And when the machine observes the world, it sees a category K of x, K1, K2, and so forth. Okay. Now they have to figure out what to do. Well, if h acts, they use a function f sub h, and it's based on the category that they're in, because they can't base the function on x, they have to base it on category of x. And similarly, if the machine delegates, then the human delegates to the machine m, it takes an action f sub m, which is based on the category it perceives. Okay, and we want to create these functions to minimize the squared loss. All right, so that's the basic model. Let's take this, and we can imagine lots of situations where we might be doing this. Let's consider this simple example just to make sure we all get the model here. So there's 2 categories, and this is the simplest possible setup, right? The human can perceive one of 2 categories, and the machine can perceive one of 2 categories. So what should we do? Well, the human notices that.
So categories are signals?
A category is you could call it a signal if you want. I mean, it basically says the world's in state x, and you could say I get a binary signal about the world, and the machine gets a binary signal. But it may not be binary, right? So it comes from this alphabet. Yes. The table is the optimal action to take. So let's call this is the F star table. So the optimal action here would be 2, well, let's say actions are numbers here.
The action's not like utilities or something.
This is a thing I should do. So I should do action, yeah.
There are 3 actions in this game, 0, 2, and 4.
Right, but they're arranged on the real line. So if I were to do, say, action 2.5, I would have to pay 2.5 minus 2 squared, because I'm trying to minimize squared loss. So an action is on the real line. The states are in some abstract space, but they produce signals. Yeah, there's not necessarily an embedding of the states. The world's in one of these 4 states, and in each state there's a real number, which is the optimal action to take. And if I take some other real number as my action, I pay the squared law. I pay the squared difference as a cost. Let's say that's the game.
Pay the squared distance to the optimal action?
To the optimal action.
Okay, so the state's the action. But
then we call these the same state. These are obviously different states. They just happen to have the same optimal action in them. Right. So there's an instance of the problem, and the instance of the problem calls for a certain action. Right. These are states 1, 1, 1, 2, 2, 1, 2, 2. 4 cells in this table. And each one has an optimal thing I should do. And if I do something else, I pay the squared difference. Makes sense? Yeah. Okay. So what would we do in this example? I guess the human notices that if they see that their category is C2, then no matter what state it is, they should do action 2. So they can actually behave optimally there. They should just do action 2. Right? Because then actions are real numbers. So So the human might as well not delegate here. And then the nice thing is that means if they delegate in state 1, I should build the machine to play action 0 here and action 4 here, because it knows it only receives a delegation request when it's in this row. Right? So a human-machine partnership could actually do this optimally at 0 error, because the human handles this, they delegate here, and the machine handles this optimally. Whereas obviously if the machine had to move first, I guess it would play the one that minimizes the average squared distance here, which would be 1, and it would play 3 here. But it doesn't have to do that if it's the recipient of a delegation request, because it's only getting delegated to here. So actually, as long as we're looking at this 2x2 version, like it feels like we could just work out the 2x2 version. Like what is the 2x2 problem? Well, 2x2 problem generically, I guess we should assume for non-triviality that that not all the rows are equal, because then the human should just do everything, right? If all the rows were equal, then the human never has any confusion. So let's assume 2 of these entries are different, and by rescaling, we can make one of them 1 and one of them 0, one of them 1. So there's 2 degrees of freedom in the 2x2 game, which is what is this optimal action and what is that optimal action, right, after we've translated and rescaled. And so there's sort of a phase diagram in the AB plane showing like what should you do at every point in the AB plane. Okay. I guess the first observation is the human should always delegate in at least one of the categories. Because if they delegate in one of the categories, the machine can play the other one optimally, because it now knows the human category it's in. So you should always delegate at least one of them. Okay. So therefore, the AB plane is going to be carved into this phase diagram that has 3 phases. Delegate category C1 when you're in C1, delegate when you're in C2, or delegate when you're in both. Those are the 3 possibilities. Okay, and so we can all kind of, try to picture like what is it going to look like. The answer is it looks like this, which is sort of not, this shape is not what we initially expected to see. And so we could back up. Okay, so I want to argue this actually ultimately makes sense as to why we get these weird shapes. And the reason is the following. So we're in the AB plane. We have those choices. And there are a couple of interesting points here. So one is the point 0, 1. If A and B are 0, 1, then this is 0, 1 and that's 0, 1. So that says you can delegate everything to the machine, because once the machine gets it, it knows to do 1 here, it knows to do 0 there. So here the loss will be 0 and the machine should do everything. The other interesting thing here is A equals B. If A equals B, we're back in the original example. The human should take category C2, give category C1 to the machine, which can behave optimally. And again, we have 0 error. So we have 0 error here, and we have 0 error here. So we have like a sort of a point with 0 error and a big trench with 0 error. And now the error grows like the square as you move away from these 2 things. And so what's that look like? This looks like a parabola growing up from here. And this looks like a cylinder growing up from here. Right? So this is kind of like we're in 11th grade pre-calculus, and you're asked to compute the intersection of a paraboloid growing up from here and a cylinder growing from here, which is some weird shape that in fact is this boundary. Right? So that's how we end up with this boundary. And far enough away, you should only delegate C2. Right? Because if A and B diverge really widely, you should let the machine do C1 where it's going to occur some bounded error. You handle C2. Okay.
But isn't it the human is choosing to delegate to the machine?
That's right. This gets back to the point about control flow, right? There are so many different possible control flows that we could study, which is one thing that makes this interesting. And we're studying one particular control flow. And that is agent 1 gets the instance, yeah.
The striped region is the...
Delegate both.
Just delegate both.
Yeah, right. And that's, the striped region is a sort of thickening of this point 0, 1, because in 0, 1 you should delegate both. And somehow by continuity, there's some region around 0, 1 where you should delegate both, and that region extends out to this little teardrop. Yeah, because on one side, it's going to be a circle. It's unconstrained on one side. The other side, it bumps into the strip, basically. Yeah. Any questions? Okay. So more generally, what's going on in this game, right? So arbitrary set of categories for the human, arbitrary set of categories for the machine. What is going on? Well, basically, the human has to pick which categories to do itself and which categories to delegate. And if it acts in category Ci, it's adding to the loss function what? A loss proportional to the variance of the values of this row. Because what will it do if it chooses to do a certain row? It's going to pick the average and then get the square distance to everything else, right? And that is the variance. So when you pick a row, you add the variance to the loss. And then having picked a row, the machine does all the columns, and it adds the variance of those. So basically what's going on is, this is the optimization problem that optimal delegation corresponds to in this, which is first we choose a set of rows to delete, we pay the variance, and then in the reduced matrix, we pay the variance in all the columns. And the question is, how do you pick rows so as to do this optimally? And the answer is actually, this is an NP-hard problem. Right, you can actually encode densest subgraph using a weighted node instance matrix. Although there are some interesting special cases where you can actually find the optimal set of rows in polynomial time. One is if the optimal action is separable. If it's a sum of something that's based on the human category plus something based on the machine category, then you can actually find the optimal set of rows. We've actually tried for a while to show something that may be true, which is that if the rows are simply positively correlated, right? If I treat the rows as vectors and just look at their correlation, if they're positively correlated, it may actually be polynomial time for all of those. It's possible. A couple of other things, but actually in the interest of getting to the other model, which I'll just mention briefly. So there's sort of this interesting landscape of possible delegates, right? So there are a few interesting functions here. One is the optimal human function, right? If the human has to do everything, there's some optimal function, f sub h. There's the oblivious machine that doesn't realize there's any delegation going on, just handles each category optimally. That's the oblivious machine. They could work together and get some performance, which if the human is delegating optimally will be better than the human working alone because it only delegates where it's going to improve the payoff. And finally, there's the optimal partner for the machine, f sub m star, and working together with them is actually going to give the best performance of all, right? So in some super high level sense, we are back to like the optimal engine and the partner bot, right? The partner bot is weaker than the optimal, but it's better when you pair them together. Okay. So, right, so we had these three key principles. I want to talk about one other model that we've looked at in the final, I think like 5-10 minutes we have. Right, so having a model of your partner to figure out what to delegate, and also the fact that actually you can create instances as you go, right? The thing you delegate can be an instance that you partly design, right? So for example, you actually see this in medical applications where in situations where the control flow is that a doctor is going to make a decision, but AI might recommend tests, right? There's an essentially infinite number of tests you could potentially run. We're not going to run them all. And so to the extent you have an algorithm helping choose the tests, that means M is now performing measurements of the world and servicing these to a decision that H then makes, right? So that's something that we can sort of imagine as a different control flow from the one that we just saw. M is providing information, H is synthesizing that into a decision. You also, in some indirect sense, see this in consumer-facing applications also, right? So a weather app, for example, there are like a zillion measurements you can take of the Earth's atmosphere that might help you, decide how to plan your day, whether to bring an umbrella, how warmly to dress, right? And some of these are sort of the ones we know, like temperature and humidity. Your weather app could, in principle, show you things like, the convective available potential energy, or CAPE, which is measured in joules per kilogram, and is the integral of how much it takes to raise a kilogram of atmospheric content out to outer space, and measures how likely storms are. I only learned about this yesterday when I asked AI to create a hypothetical weather app that would have really weird meteorological measurements on it. So sadly, you can't download this app because it doesn't exist. Similarly, the solar irradiance, which is the global horizontal irradiance, which is the watts per meter squared falling on the Earth, also apparently a very useful thing for planning your day. If only you knew how to use it. Like, I don't really know how to use the CAPE, but apparently it's super useful for predicting storms. So there are lots of things you could show. I could show the temperature, I could show the humidity, I could show this thing that's apparently called the CAPE. And so in this work with Gali, Kate, and Sigal, we thought about like, okay, so what is the problem faced by this intelligent weather app? Again, there's a state of the world, and now we'll actually use a slightly different model. It's not just a single atomic state descriptor. Let's say it's described by features. And I'll pick sort of the simplest version of the model we studied because we only have a few minutes left, and I wanted to show you a few things that we can process in real time. So the state of the world is described by features x1 to xn, which are all independent random variables with mean 0, variance 1. There's an optimal action, we're again thinking about actions, which is given by some linear function of the features. Okay, so it's just sum of AI xi. Now, the human is going to receive these measurements, and if they knew the AIs, then somehow this would be just, then the human and the machine would be working perfectly in tandem, because the machine is just providing measurements that are going to be optimal, subject to the human's budget on attention. But the human is wrong, and they believe the coefficient on xi is hi rather than ai. Right, so if you have never heard of the CAPE and someone shows it to you and tells you it's 650 joules per kilogram, you don't know how to use that. So your estimate of how it affects your plan is probably not the optimal estimate. Whereas if you've lived your whole life with temperature, if someone tells you it's 84 degrees, you know exactly how to dress when it's 84 degrees because you've lived your whole life hearing temperatures in Fahrenheit, assuming you grew up in the United States. Okay, so now the problem is M has to pick a set of features to show to H. Let's assume it even has estimates of AI and HI. But it has to somehow balance now between some features are useful and some features the human knows how to use well. And how do I balance those two things? If my goal, right, the human will take this action based on their coefficients, and I want to minimize the mean squared error of what happens. So what's going on is something that in the paper we call this informativeness divergence trade-off, right? You're trying to simultaneously optimize two things that are in tension. You want features where AI is large, because that's the truth, but also where the difference between the human's belief and the real thing is small. So here's a little worked example where, for example, the most informative feature is one where the human is super wrong, so you want to avoid the most informative feature because the human's going to misuse it, right? Our basic model has been set up to kind of be extremely tractable because these are independent random variables of unit variance, which means that every time you omit AI from your set of measurements, you're going to incur an error of AI squared because that is the variance. And whenever you include something in the set A that you show to the human, you're going to incur an error that's based on the squared distance from the human's use of it to the real use of it. And that suggests is actually, for the simple model I'm showing you right now, there's an optimal way to pick these K features that you're going to put on the screen of the weather app, which is to sort them by AI squared minus AI minus HI squared, because this is the loss reduction you get, but it's subtracted by the loss you incur through the misuse of the feature. Okay? And if I just sort these, then that is how I'm, in this very stylized structured case, how I'm managing the informativeness divergence trade-off. Now there's one extra thing going on, right? So your weather app loads up this thing, and over time you're like, I'm finding the CAPE pretty useful. This integral of how many joules it takes to raise a kilogram of atmospheric content out to outer space really is helping me get a sense of when storms are brewing. It's quite helpful. And the point is, like, my coefficients are updating. I'm getting better at using the CAPE on my weather app. So let's imagine that the features, this is going to happen over a series of time periods, right? We're going to use the weather app each day. And so I have incorrect beliefs, but they're time parameterized. So my belief about the coefficient on I is h sub I comma t. And so it's changing. At time t, it's different than it was. And we're going to choose the action based on my current estimate of this. And we want to argue that the human gets better at using these features. I don't want to presume a certain way in which humans are going to learn to use features. So let's take some abstract formulation, which is the distance at time t of my coefficient to the true coefficient is just going to be is going to start at what it was originally, and then it's going to be times some monotone decreasing function of the number of times I have seen this feature in use. Right? If you never show me the CAPE, I don't get better at using it because I've never seen it. If you show it to me a bunch of times, I'll incur error, but I will get better at using it. Right? It's going to go down by this arbitrary function phi, monotone decreasing function of how many times I've seen it. Question?
What if you pick a feature where A minus H is not small, it's fairly large, but,
yeah.
But there's an explanation as to why that feature is important to the human.
Yeah, it's a great question. Right, so like there's an interesting potential way to add some notion of like explainability into the story, right? That this is just through repeated exposure I'm getting better at it. But it is true, when I asked Gemini to mock up the weather app, it does tell me that like stability, it's weakly unstable, it's like trying to tell me stuff. It actually didn't write the letter E right because it's trying to produce pixels and these aren't letters, but that's just a separate issue. So yeah, no, I think there's a nice way to try adding an explainability component to this. Like here is the model without explainability, but maybe with explanations you could argue how much quantitatively do I gain by doing that? It's a great question. Okay, and so the goal is to minimize my total mean squared error over all time periods where time is now discounted by this delta to the t parameter. Now, as in any economic model of decisions over time, delta represents your patience, right? If delta is close to 1, then you really care about the long future. And if delta is, near 0, you just want to get this to work now, right? So like if I'm demoing the weather app to you, and you're like, what the heck is the cape? I hate this weather app. That's kind of like delta equals 0. It only has to work in this period because it's a demo. If I really am going to use this weather app over 365 days, maybe I'm very patient. It's okay if it takes me a while to learn how to use this feature. Okay, and so that's what's going on here. There's a delta, and actually, this is a worked example that not so crucial, but you sort of get the idea, right? That if time is going to end today, I should show you the one that's attuned to your wrong beliefs today. But as delta gets very close to 1, delta will eventually get close enough to 1 that I should actually show you the most informative feature set, because you will eventually learn to use it. And so this second trade-off, right? Informativeness versus divergence was one. The other is what we called, this thing from business school courses around the world, the fixed versus growth mindset, right? The question is, do you believe, right, does the machine M, in showing you these measurements, believe that the human is a static partner who just has the abilities they have, in which case they're going to optimize for that? That's the fixed mindset. Or do they have this growth mindset in which we're going to encourage learning despite a lot of initial mistakes that get made? And the answer obviously depends on delta. If this is a one-shot interaction, then growth, you're not benefiting from growth in the objective function. And if it's a long interaction, then you are benefiting from growth. And so just a few theorems to mention in this model, and then I'll wrap up. So again, humans' beliefs are getting better according to some arbitrary monotone decreasing function that's limiting to 0, where, the difference is limited to 0. The first one is this thing which, again, is sort of intuitively clear, that for large delta close enough to 1, you should actually show the most informative feature set, because the human will eventually learn. A slightly more surprising fact in this model, and again, this is very much about this model, is that for every delta, the optimal strategy is to actually present the same sequence each time. In the model, as we've set up, there's no gain in kind of swapping in and out features. You should pick one, get the human to learn it, and do that. And finally, so we have a bunch of fixed feature sets, right? So how many versions, as we sweep over all delta, right? There's the person who's going to use it for 1 day, 2 days, 3 days, 4 days, 365 days, so forth. As we sweep over all deltas, how many different, home screens do we get on the weather app? And the answer is the number of times the optimal set changes is at most n choose 2, which is the number of features, plus k, which is the size of the available real estate for showing measurements, right? I can show up to k measurements. And this is roughly because there's an initial phase with very low delta where I might actually populate the thing. Because if you misuse things extremely badly, there might not even be k features to show you, because you might misuse them so badly. And then once it's fully populated, then essentially each pair can cross once. Each measurement can kick out each other measurement at most once, and we get this bound here. Okay, and that brings me to the end, right? So in the end, there are these principles that we were sort of trying to capture in these models. Somewhere in a middle slide of the talk, I mentioned a whole bunch of related theoretical references that were sort of inspiring us as we went on this. Right, this idea of like deciding which instance to delegate, having a model of your partner. You can craft the difficulty of the instance you delegate, and finally, your partner can actually learn, right? This growth mindset. I think there's a whole bunch of questions here. Maybe the second of these sums up a lot of them, which is, as this is making clear, and as we've seen from a number of the other talks, there's so many different control flows for partnership and delegation in this setting that it would really be interesting to try finding a way to unify all of these things, right? I think there are very interesting results in a lot of these models, but this proliferation of models is partly because we sort of learn different things from different configurations. Now that's partly inevitable because there really are just many different ways that we're going to partner with algorithms as we go about solving tasks. But finding commonalities in these models, I think is a very, very interesting kind of question. And then of course, there are many other things we could ask. Obviously, things here were perfectly specified. When we have misspecification, we get even more complicated situations, right? What if the weather app doesn't have a good model of your beliefs about how to use these things? Then we're going to start off from a different initial state. And similarly, this has been sort of an incentive-free description of the world, right? As in, this machine, or whoever's making the machine, is perfectly focused on you solving the task as well as possible. But maybe it's less important for the weather app that you plan your day correctly than that you use the weather app, right? Those two incentives might be misaligned. Or maybe in the thing you're delegating to, it wants to get delegated to. It wants to maximize the number of situations where it gets delegated to. And that may be different from optimizing the human plus machine performance. And so I think all of these are going to be really interesting questions to think about. And I think obviously workshops like this, which have been really fascinating for me, are a really interesting way to synthesize the many different approaches that there are to modeling these questions, and to maybe hopefully arrive at some synthesis that maybe all of us as a community can take going forward. Thanks very much.
A couple of questions, just start passing back.
I was wondering, this seems very related to kind of AI alignment more
Yep.
generally, and how do you, just where do you place it in that space of what we're used to thinking about to the stuff you're talking about here?
Yeah, I mean, so I think to kind of go in order, the chess thing I think is very much a kind of alignment in the sense that I'm trying to get the chess partner to put me in situations where I'm not going to mess everything up. I mean, it's alignment in the sense that, all of these have the property that the human is in control of something, right? That's a common theme in all of these. Obviously, we can also speak of alignment in situations where the human is in control of nothing except to kind of hope for a good outcome, right? We can also ask about alignment in those situations. These models don't cover that, right? In a world where the AI is running fully autonomously in an unturn-offable way, we can still ask whether it's aligned with my preferences, but my preferences are sort of inert in the sense that I can't influence the outcome. So I would say it relates in the sense that all of these are different situations, different places of saying, here's where the human has agency in each of these models, and is the AI aligned with allowing the human to use their agency as well as possible? Yeah, Jason.
Yeah, in the last thing you were talking about, you had a result about whether you show a fixed set of features or whether you vary the set of
Yeah.
features. And I'm not sure about your model of what you're signaling if you can vary the figures, because there's a signal in what you choose to show.
Yeah. That's a great question.
And so can you say...
Yep, great question. So as you're pointing out, the model we have here is the human is not executing an arbitrary strategy. The human is simply taking the features it's given and using the coefficients they have. And they're not doing any other computation. If they could do additional computation, now we have a very complicated problem, because I could be showing you a very slow bit string that's telling you something. Yeah, and this gets back to the question about explanations, right? I could also just inline an explanation. If I was trying to do that, I may just want to inline an explanation.
Okay, so then maybe I can ask a clarifying question then, because I would have tended to ask questions like you're asking in an information theoretic setting where there's a signal, you page an update, you take the posterior optimal action given your signal.
Yeah.
That seems to be not your model.
Yeah.
So what's your model?
The model is just the algorithm shows measurements, and the human just plugs them in to using their coefficients, right? So
the human pre-computes some coefficients,
the
not
human
knowing what subsets of things are going to be available. I assume you mean center them, so if you don't see a thing, then it's sort of neutral.
Yeah.
And then you just use the best, okay.
Yes, that's correct. That's our behavioral model of what the human is doing. Yeah. I mean, we could imagine that you believe your weather app is sending you coded messages each day, and you carefully write them down, and you go, yep, my weather app is trying to communicate to me this very slow bit string about something, but we're imagining a behavioral model in which humans don't do that with their weather app, for example. Yeah.
So I'm trying to understand where the misalignment comes in, because it feels like to some degree, in my mental model, the human actor just wants to be as accurate as possible, and so the only way you're going to keep them using the platform or the tool, as opposed to other maybe competitive tools, is by making it better in terms of accuracy. If I read my weather app and it tells me it's going to rain outside and it's not raining, then I'm going to be really annoyed that I didn't bring my, I guess I wouldn't be annoyed if I did bring my raincoat. If it was the other way around and I get stuck in torrential rain, I'm going to be annoyed. I'm going to switch to the better app.
Yep.
So can you talk about that a little bit?
Yeah, so this is a question that we talked about, and so they're more complicated models than the ones I put up here from the work, where we thought about, imagine two possibilities. One is I have some kind of impatience where if I expect to get a certain level of utility, and if I don't get that, then I'm not happy with the weather app. In which case, we now have a different objective function, right? We don't have this infinite discounted sum, but we have I need to keep using it. And then you could have a competitive environment. There are two weather apps, and they're competing for your attention. And then presumably the one that kind of gives you the most immediate gratification, if you start using it, it can then lock you into that. So I think the version where there are competing versions of this, you could get interesting results, presumably pointing to a kind of suboptimality that you don't get in the case of a single one. Yeah, that's very interesting. Yeah, you had a question also. Yeah.
Sorry, I'm sort of trapped.
Thank you. All right. So one thing that so across both the chess setting and the weather app setting, it seems like there's kind of like there's this fundamental asymmetry between like the strong model and the weak model, which maps onto like the agent and the human.
Yeah.
And part of that is that there is sort of this like world model asymmetry in the sense that the strong model has a good model of the weak model, and the weak model basically has no model of the strong model. And so I'm wondering if like you've thought at all about kind of relaxing that assumption a bit on the part of the weaker model, because I'm trying to think about like an interaction with a large language model where we might have some sort of like fuzzy contours of what it's good, what it's not so good at, and if that can maybe buy you something in these kinds of settings.
Yeah, that's a great question. I think in the situations we're thinking about, the weak agent having limited knowledge of the strong agent is somehow inherent in the sense that we're imagining that this is a problem that's sort of too hard for the weak agent to solve on their own. And so there's sort of almost a triangle inequality that like the strong agent has a good model of the world. If the weak agent had a very good model of the strong agent, then by some kind of triangle inequality, it would also have an approximate model of the world, which,
it would also be
and our basic assumption is that it doesn't. And so I think that's sort of the starting point. I agree that, we often deal with large language models, so for example, if I ask a large language model to solve a task that's way beyond me, I would argue that despite the fact that it then presents it to me using, a lot of really polite words, I still don't really have a model of what it did. On the other hand, as you're pointing out, there are tasks where maybe we're on more even terms, like we're discussing something and we both have a similar understanding of it. And then I think it is very interesting to ask about how the world models that we have align, and that would be a different set of questions than we have here, but a very interesting set of questions, absolutely.
Hey, thanks so much. I wanted to ask, for the partner bot work, did you think at all about overfitting to the partner, or the extent to which that might be a challenge arising? Like there could be like, there's the problem of playing with a random person that has that ELO, and then there's playing with a specific
and I think
bot.
that is going on here actually. That this gets very good at playing with Maya. It is less clear it gets good at playing with every possible 1500 rated player. And we've done some attempts at experimenting with this where we try to have different flavors of Maya. We look at, that is definitely an issue. I mean, there are other things going on here. Like, there's a whole bunch you could say about this one slide. Like, obviously, the partner bot surely is also learning how to create difficult situations for the opponent's Maya partner. That must be going on also. Right, but it's sort of an interesting, like, intuitively, it's sort of like a high school coach and 2 high school basketball players go out to play 2-on-2 basketball, and the 4th player is an NBA player. And the 2 teams are going to be the high school coach and one of their players, and the NBA player and the other player. And you could ask legitimately who's going to do better in that situation, because obviously the NBA player has absolutely no idea how to play with this high school player. Right. On their own, they're obviously way beyond everyone else. Whereas the high school coach and the player have worked together for like 3 years, and they know exactly all their exact, insert basketball terms I don't know here, but like they know exactly what to do. And then the question is like, to your question, is the high school coach, they're particularly attuned to playing with their high school player. If you gave them a random high school player, that would not necessarily be the same partnership. Yeah. So I think all of these are probably going on here. Yeah.
Okay, great. Thank you.
Yeah.
Okay, let us call it an afternoon, at least for this part. We will have our panel upstairs in just under an hour, so at 3:45. So you guys can.
It's on the second floor?
On the second floor, yes. There will be a seating area set up. I don't know exactly where, but in the big common area somewhere. It should be obvious. We'll figure it out. If there's a pile of us, you'll know you're in the right place. Anyway, let's thank John. Thank you for the excellent talk. And panel should be fun.